93 million miles away, a star that has burned with roughly the same quiet reliability for 4.5 billion years is right now in one of the most turbulent stretches of its current 11-year cycle, firing off X-class flares in rapid succession, hurling clouds of magnetized plasma across the solar system, and doing all of this at the exact moment a small, ancient fragment of ice and rock is diving directly into its atmosphere. Meanwhile, 93 million miles closer to home, on the very same planet that star keeps alive, the ground has been shaking in bursts across Southeast Asia, a swarm of earthquakes releasing energy in a pattern seismologists have seen many times before. And overhead, further out than either of those events, a crew of astronauts is currently in transit, exposed to more of that solar radiation than anyone standing on Earth's surface will ever have to face. None of these things are connected to one another by any mechanism modern physics recognizes, and yet, all of them are happening at once, in the same narrow window of time, and all of them are part of a genuinely larger, genuinely important story. The story of how exposed human civilization actually is, right? Now, to the physical behavior of the star we orbit, and how much of what is coming, in the very real, measurable sense, is going to reshape how seriously we take that exposure going forward. This is the story of what is actually happening in space right now, separated carefully from speculation, and why the honest version of this story is dramatic enough on its own terms that it never needed exaggeration to matter. Start with the sun itself, because everything else in this story depends on understanding the specific phase of activity it is currently moving through. The sun operates on an approximately 11-year rhythm of rising and falling activity. Astronomers call it the solar cycle. And the current one, solar cycle 25, has proven considerably more active than early forecasts predicted, reaching a maximum that outpaced official projection, by a wide margin. During this kind of active stretch, individual sunspot regions, the darker, magnetically complex patches that occasionally form on the sun's visible surface, can produce a rapid, repeated sequence of flares within the span of just a day or two. Flares are classified by strength using a letter and number system, with X-class flares, representing the most powerful category, each whole letter step representing roughly 10 times the energy of the class below it. A single active region producing multiple M-class and X-class flares within 24 hours. Exactly the kind of activity space weather forecasters have documented from specific sunspot groups during this stretch of the cycle is a genuine, well-established signature of a region capable of producing something considerably larger. That something larger is a coronal mass ejection, an actual physical cloud of magnetized solar plasma, billions of tons of material hurled outward into space, distinct from the flash of radiation a flare produces. Where a flare's light reaches Earth in about 8 minutes, a coronal mass ejection takes 1 to 4 days to physically arrive, and when it does, it can trigger a geomagnetic storm, a disturbance in Earth's own magnetic field ranked on a 5-step scale from G1, minor, to G5, extreme. Recent activity from this solar cycle has already produced a real G3, strong-level geomagnetic storm, arriving with enough speed that it spiked conditions quickly before settling back toward calmer levels within about a day. A documented, measured event rather than a hypothetical one. Layered into this same active stretch of solar behavior is a genuinely rare astronomical visitor. A Kreutz family sun-grazing comet, a fragment of a much larger parent comet, the T, broke apart in a previous close pass by the sun, centuries or millennia ago, now making its own extraordinarily close approach, its perihelion, the point of closest approach, bringing it to fly directly through the sun's outer atmosphere, the corona. Sun-grazing comets are, by their nature, high-stakes objects to track. Some survive their pass around the sun, emerging on the far side to potentially become spectacular naked-eye great comets. Others do not survive at all, vaporizing completely under the combined stress of extreme heat and gravitational tidal forces. Which outcome a specific comet experiences depends heavily on its size and internal cohesion. Factors that remain genuinely difficult to fully assess from Earth-based observation until the comet is already deep into its solar encounter. There is a documented historical instance worth including here, precisely because it illustrates a real, if still not fully mechanistically settled, area of active scientific inquiry. Archival spacecraft imagery from 2011 shows a small sun-grazing comet diving into the sun with a coronal mass, the ejection recorded launching from roughly the same region shortly afterward. It is important to be precise about what mainstream heliophysics actually concludes from that kind of coincidence. The dominant scientific view holds that a comet, even a reasonably substantial one, carries far too little mass to meaningfully disturb the sun's own vastly more powerful magnetic systems, and that these apparent coincidences are most likely the product of two independent solar system events occurring in temporal proximity rather than one causing the other. A conclusion supported by the simple fact that the overwhelming majority of coronal mass ejections occur with no comet involved at all, and the overwhelming majority of sun-grazer disintegrations produce no associated eruption whatsoever. That correction matters, not to diminish the genuine drama of a comet flying directly through the solar corona, which remains a remarkable event in its own right, but because getting the actual physics right is part of taking the story seriously, rather than merely making it sound more dramatic than the evidence supports. What is not speculative and does not require any contested mechanism to explain is who is actually exposed to the consequences of this heightened solar activity right now, in the most direct physical sense. Astronauts currently in transit through deep space, well beyond the protective bulk of Earth's atmosphere and magnetic field, are exposed to space radiation at levels dramatically higher than anyone on Earth's surface, or even in low Earth orbit ever experiences. The International Space Station sits low enough that Earth's magnetosphere still provides meaningful shielding. A spacecraft in transit between Earth and the Moon has no such protection, and elevated solar particle activity during exactly this kind of active stretch of the solar cycle represents a genuine, well-documented operational hazard that mission planners take seriously, tracking proton flux levels and radiation storm thresholds, specifically because a strong enough event could pose a real risk to crew health during transit. That is not a hypothetical concern invented for dramatic effect. Space agencies maintain continuous monitoring of solar proton flux precisely because a sufficiently severe radiation storm, even one falling short of the most extreme classification thresholds, represents genuine elevated risk for anyone outside Earth's protective magnetic bubble. Crews currently in transit through this environment are, quite literally, flying through a more energetic version of space than astronauts have had to contend with during quieter phases of the solar cycle, a real, physical, measurable exposure that has nothing to do with speculation and everything to do with basic radiation physics. Meanwhile, back on the planet, these astronauts left behind, a separate, entirely unrelated natural process has been playing out across the same general window of time. A documented earthquake swarm across Southeast Asia, a sequence beginning with a major main shock and followed by dozens of aftershocks, several themselves reaching significant magnitude, part of a broader pattern seismologists have studied for decades. This kind of swarm activity, a large release of tectonic energy, followed by an extended sequence of aftershocks gradually declining in frequency and magnitude over subsequent days and weeks, is a well-understood, well-documented feature of how stress redistributes along and near a fault system after a major rupture. It requires no connection to solar activity, planetary alignments, or any other astronomical coincidence to explain. Tectonic plates store and release stress according to their own independent, geologically driven timeline, entirely separate from whatever the sun happens to be doing on any given day. The temptation to connect these threads, the active sun, the sun-grazing comet, the earthquake swarm, the exposed astronauts, into a single unified narrative of cosmic cause and effect is an old and remarkably persistent one in human storytelling, and it is worth understanding honestly why that temptation exists, rather than simply dismissing it. Human pattern recognition is exceptionally good at noticing when several dramatic, newsworthy things happen within the same narrow window of time, and exceptionally bad, on its own, at correctly weighing how often that kind of temporal clustering happens purely by chance, given how frequently solar flares, earthquakes, and comet passages each occur independently across any given month. The sun produces flares constantly at every phase of its cycle. Earth experiences earthquakes constantly, dozens of magnitude 4 or greater, somewhere on the planet every single week. A clustering of newsworthy solar and seismic activity within the same few weeks is not a rare connected anomaly requiring a shared explanation. It is close to the statistically expected background behavior of an active planet orbiting an active star, made to feel more remarkable than it actually is by the simple fact that modern global monitoring and media coverage now makes us aware of far more of these individually ordinary events, happening simultaneously across the entire planet, than any observer in an earlier century could ever have tracked at once. That does not make any of these individual events any less genuinely significant or worth understanding carefully on their own terms. An active solar cycle producing real, measurable geomagnetic storms is a legitimate subject of ongoing scientific monitoring, precisely because those storms carry real, well-documented consequences. Induced currents capable of straining power, grid transformers, degraded GPS accuracy, disrupted high-frequency radio communication, and genuine elevated radiation risk for astronauts and, during the most extreme events, even for aircrew flying polar routes at high altitude. A major earthquake swarm is a legitimate subject of seismological study and regional disaster preparedness, independent of anything happening in space. A large sun-grazing comet surviving, or failing to survive, its closest approach to the sun is a legitimate, fascinating subject of astronomical research in its own right. offering real scientific insight into comet composition and behavior under extreme conditions. Each of these threads deserves to be taken seriously and followed closely using the actual scientific tools built specifically to study it, rather than being flattened into a single, less accurate, more dramatic story that borrows urgency from all three at once, without correctly explaining any of them. What genuinely is coming, in the most defensible, evidence-based sense available, is not a single, unified cosmic event, but a continued stretch of the kind of heightened solar activity that tends to accompany this phase of the solar cycle, activity that carries real, well-understood consequences worth preparing for seriously rather than mythologizing. Space weather forecasters expect continued elevated flare and storm activity for as long as the current active stretch of sunspot regions remains oriented toward Earth, a window measured in days, no T-months, before those regions rotate around the sun's far side. Grid operators, satellite companies, and space agencies operating human missions in deep space all factor this kind of activity into real, practical operational planning, because the consequences, unlike speculative cosmic narratives, are genuinely measurable and genuinely consequential for the infrastructure and people directly exposed to them. That distinction between what is genuinely, verifiably coming and what is simply a compelling story stitched together from unrelated coincidences matters for a reason beyond scientific accuracy alone. Solar storms capable of damaging power grids, satellites, and communication infrastructure are a real documented category of risk that grid operators, satellite engineers, and space agencies plan around using rigorous physics-based forecasting models in the public. Conversation around that real risk is better served by understanding it accurately than by wrapping it in unrelated, unverifiable narrative elements that, however emotionally compelling, do nothing to actually improve anyone's preparedness. A grid operator deciding whether to take a transformer offline during a forecast, G3 storm needs an accurate physical model of incoming plasma density and magnetic field orientation, not a narrative about planetary alignments or a comet's symbolic significance. An astronaut's mission planners need precise radiation dosimetry data, not a poetic framing of the sun's intentions. That is, in the end, the most honest way to answer the question this story's title poses. What is coming that could genuinely change how humanity relates to its own star is not a single mystical cosmic event arriving on a specific date, timed to some larger unseen design. It is the accumulating entirely real evidence that modern civilization has built itself over the past century into something considerably more vulnerable to ordinary well-understood solar physics than most people realize day to day. A civilization running on satellite-dependent navigation, an interconnected electrical grid sensitive to induced currents, and, increasingly, human missions spending extended stretches of time beyond the protective shell of Earth's own magnetic field. Exactly the vulnerability currently being tested in real time by the very active stretch of the solar cycle unfolding right now. Taking that vulnerability seriously does not require comets to carry hidden messages or the sun to hold intentions toward the astronauts currently in its glare. It only requires taking the actual measured physics seriously enough to keep building the forecasting, the shielding, and the infrastructure resilience that this stretch of solar activity is currently demonstrating, in the clearest possible terms, that we still have real work left to do. The comet will either survive its plunge through the corona or it will not, and within days, observers on Earth will know which. The current sunspot regions will either produce the larger X-class flare forecasters have flagged as increasingly likely, or they will rotate quietly around the sun's far side without incident. The earthquake swarm across Southeast Asia will continue its statistically expected decline in aftershock. Frequency, the way seismic sequences reliably do. None of these outcomes are connected to one another by anything more than the calendar they happen to share. But together, honestly examined, they tell a genuinely important story anyway, not about cosmic destiny, but about how much of what shapes human civilization's future vulnerability to space weather is already, right now, being measured, tracked, and understood by scientists working carefully with real data, and how much still depends on whether the rest of us choose to take that real, unglamorous, thoroughly explainable science as seriously as it deserves. It is worth walking through exactly how forecasters actually track and predict this kind of solar activity, because the real infrastructure behind space weather prediction is, in its own quiet way, just as remarkable as any of the individual events it monitors. A network of spacecraft positioned at strategic points around the Sun and Earth continuously feeds data back to agencies responsible for issuing space weather alerts, tracking everything from the Sun's visible surface activity to the density and speed of the solar wind as it streams outward. One of the most critical of these outposts sits at a location called the First Lagrange Point, roughly 1 million miles sunward of Earth, a spot where the gravitational pull of the Sun and Earth balance out enough for a spacecraft to hold a stable position relative to both. Instruments stationed there act as an early warning tripwire, sampling the actual speed, density, and magnetic orientation of incoming solar plasma as it physically passes by, typically providing somewhere between 30 and 60 minutes of genuine advance, warning before that same material reaches Earth, a narrow but operationally critical window that grid operators and satellite teams use to shift into protective postures before an incoming storm actually arrives. That monitoring infrastructure exists because the consequences of getting caught unprepared by a genuinely severe geomagnetic storm are well documented in the historical record, not speculative. In March of 1989, a strong geomagnetic storm induced currents in Quebec's power grid severe enough to trip protective relays and black out the entire province for roughly 9 hours, affecting millions of people in the middle of a Canadian winter, a real, measured demonstration of exactly the kind of infrastructure vulnerability this story has begun describing throughout. In 2003, a series of storms nicknamed the Halloween storms damaged satellites, disrupted airline navigation and communications, and caused a brief power outage in Sweden. These are the reference points space weather forecasters use when calibrating what a strong or severe storm might realistically mean for a modern, satellite-dependent, electrically interconnected society, drawn not from speculation about what could theoretically happen, but from documented events that already have. The astronauts are currently exposed to this. Heightened solar activity are protected by exactly this kind of careful, physics-based monitoring and planning, rather than by chance. Mission planners track proton flux and radiation storm thresholds continuously throughout any deep space transit, maintaining contingency protocols specifically for scenarios in which solar activity exceeds safe thresholds during a mission, including options for altering spacecraft orientation to maximize whatever shielding the vehicle's own structure can provide, or, in more extreme scenarios, adjusting mission timelines around forecast periods of especially heightened risk. None of that protection depends on the sun's intentions or any kind of cosmic mercy. It depends on decades of accumulated solar physics research, a global network of monitoring spacecraft, and mission planners who take radiation dosimetry as seriously as any other life-critical system aboard their spacecraft, precisely because the physics involved is well enough understood to plan around rigorously, even without being able to predict every individual flare's exact timing in advance. That same rigor extends to how researchers are approaching the sun-grazing comet currently making its own close pass by the sun, an event genuinely worth following, closely on its own scientific merits, regardless of whatever solar activity happens to be unfolding alongside it. Comets that survive a sufficiently close solar passage offer researchers a rare, direct opportunity to study material that has remained largely unchanged since the early formation of the solar system, suddenly exposed to extreme heat and radiation, in a way that reveals its internal composition through the specific gases and dust it releases as it warms. Comets that do not survive still provide valuable data, their disintegration patterns helping refine models of how loosely bound icy bodies respond to the combined stress of solar heating and gravitational tidal forces at extremely close range. Either outcome adds genuine, useful information to the broader scientific understanding of these ancient, fragile visitors, independent of whether the comet happens to share a calendar with an active stretch of the solar cycle or not. Perhaps the most useful habit for anyone following stories like this one, as new solar and seismic activity continues to make headlines in the weeks and months ahead, is learning to hold the genuine excitement of a dramatic, multi-front natural event alongside a clear-eyed understanding of which parts of the story are rigorously measured and which parts are speculative narrative layered on top. The sun really is unusually active right now. A genuinely rare comet really is making an extraordinarily close pass through the solar corona at this very moment. Astronauts real Y are flying through measurably elevated radiation exposure during their transit. An earthquake swarm really has released a significant amount of tectonic energy across Southeast Asia in recent weeks. Every one of those facts is dramatic enough and important enough to deserve serious, sustained attention entirely on its own merits, without needing an invented cosmic thread stitching them into a single, tidier, more mystical story than the evidence actually supports. What is coming, in the truest, most defensible sense, is simply more of exactly this: a genuinely active sun, a genuinely active Earth, and a species increasingly capable of measuring, forecasting, and preparing for both, provided we keep choosing to trust the instruments over the instinct to see a hidden pattern where none has yet been proven to exist.